investigate the convergence of the integral between 1 and infinity, positive infinity, of 1 over x to the p dx with respect to x, where p is a real number, right? So there's an improper interval. We are going to investigate this by trying to evaluate the integral. We're going to consider certain cases of p. We're going to consider, well, when p is 1, what happens? When p is more than 1, what happens? And when p is less than 1, what happens? And it's going to lead to a very important result, which you will be able to use and quote when investigating convergence of other things. So it is very useful. Right, so the integral, I'm going to call the integral I equals, well, it's the limit as b approaches infinity of the integral between 1 and b of 1 over x to the p dx. So that form is fine for the first one if we just consider if p equals 1. So if p equals 1, so that makes the integral really simple. The integral becomes the lim as b approaches infinity of the integral between 1 and b of just 1 over x dx. So that's one of our standard integrals. We know that 1 over x integrates to ln x, the natural log of x, with respect to x. So that equals the limit as b approaches infinity of ln x evaluated at 1 and b. Right, so that equals the limit as b approaches infinity of ln b minus ln1. Well, ln1 is easy enough, that's just 0. Remember the power you raise e2 to get 1, so that's just 0. So this now equals the limit as b approaches infinity of ln b. So, you know, basically natural log of infinity, what do you raise e2 to get infinity? Well, this limit doesn't exist. There's no nice value that we're approaching. It's just getting bigger and bigger and bigger. So this does not exist. Does not exist. And if the limit doesn't exist, then the integral diverges. So the integral between 1 and infinity of 1 over x to the p dx diverges when p equals 1. Okay, so I equals the limit as b approaches infinity. Now I'm actually going to have to do a bit of work on this, so we're just going to write this in the index form. Between 1 and b of, well, it's x to the power minus p, 1 over x to the p, x to the power minus p dx. Right, so if we integrate that, remember it's a nice standard one when you're integrating a polynomial, you add 1 to the power and you divide by the new power. So this equals the limit as b approaches infinity of, well, this is going to be x to the power minus p plus 1. So I'm going to write that as x to the power 1 minus p, x to the power 1 minus p, and then just divide by that same power, so 1 minus p, right? And that needs to be evaluated at 1 and b. Equals the lim as b approaches infinity of, well, it's b to the power 1 minus p over 1 minus p, minus 1 to the power 1 minus p over 1 minus p. Okay, so that's a bit messy, but we can certainly make it better. So what we can do, if you look at it, you've got a 1 minus p in both. Remember, it's b is the letter that's approaching something, so anything else can be classed as a constant unless it's affecting the b. So we can definitely pull this 1 over 1 minus p out as a common factor. And you can also think about what is 1 to the 1 minus p. Well, 1 to, you're going to raise 1 to any power, it's going to remain 1. So this can now be 1 over 1 minus p times the limit as b approaches infinity of, well, it's b to the power 1 minus p minus 1. Okay, so looking at the form we've got it in, I'm going to consider the case where p is less than 1 first. Okay, so if p is less than 1, well, that means 1 minus p, which is the power that we're raising b to, is going to be positive, greater than 0, is positive, right? So that means as b approaches infinity, b to the power 1 minus p also approaches infinity. So even if, say, p is somewhere between 0 and 1, so say p was 0.9 even, something like that, even if we end up with b to the power of 0.1, because b is such a large number, it would still be approaching infinity. So I hope that clears that bit up. So if this bit is approaching infinity, so that means that the limit doesn't exist. Therefore, the limit does not exist, as it's not approaching a finite number, and that also tells us that the original integral, so integral between infinity and 1 of 1 over x to the p dx, it tells us that diverges when p is less than 1. Right, so now if I consider the final scenario when p is greater than 1, what I'm going to do, I'm just going to rewrite this in a form that's more useful. So when p is greater than 1, I'm just going to just change this b to the 1 minus p term and use a reciprocal. So the integral could also be written like this, equals, I'm going to stick with this 1 over 1 minus p, 1 over 1 minus p times the limit as b approaches infinity of, well, what I'm going to do, instead of writing b to the power 1 minus p, I'm going to write the reciprocal of b, so that's 1 over b to the power, or to the negative power, so to the power of minus 1 minus p, which would just be p minus 1. So 1 over b to the power p minus 1. It's completely equivalent, just taking the reciprocal and times the power by minus 1, and this minus 1 is still there, right? And then we could also rewrite this using one more line, so equals 1 over 1 minus p times the limit as b approaches infinity of, well, 1 to the power of p minus 1 will just be 1, so 1 over b to the power p minus 1 minus 1, just like that. And now we can look at it. So when p is greater than 1, p minus 1 is going to be greater than 0, right? And in a very similar way to when we looked at this, and b to the power of p minus 1, well, that is going to approach infinity in the same way. Remember, even if p minus 1 isn't very positive, even if it's, say, 0.01, something like that, we're still raising infinity to a positive power. It still approaches infinity, right? So that means 1 over b to the power of p minus 1, well, that now is going to approach 0 because it's 1 divided by a really, really big number. So that means that the integral is going to approach, well, 1 over 1 minus p times, well, we've just said this is 0 minus 1. So that would be 0 minus 1 equals, we can put the minus 1 anyway, so we just put it in the bottom. So that's going to be 1 over p minus 1, which isn't necessarily important what it's converging to. The point is the fact that it is converging. So the integral between 1 and infinity of 1 over x to the p dx converges when p is greater than 1, and it diverges when P is less than or equal to 1, and this is called the P series, and you can use it to evaluate convergence of other things if you can get them into a P series. We'll see more examples on it.